hope after doing those problems and the one on the homework quiz where you write the equation that you feel comfortable with this formula now. A times b to the x is our exponential formula, where a is your initial value, b is your, what do we call that? The base. And it says if your function has a is greater than 0 and b is greater than 1, then it will always be increasing. And think about exponential growth kind of looks like this, right? So it's increasing as x gets bigger, y gets bigger. And they say if b is greater than 0, then it will be exponential growth. As opposed to if b is less than 1, those are kind of the big differences here. And by less than 1, I don't really mean like a negative number. I mean like a fraction, right? If b was 1/2, or b was 1/4, or if b was any fraction smaller than 1, then it's going to be a decreasing function, and it's going to be exponential decay, which means as x gets bigger, y actually gets smaller. And you could draw a little picture next to that that would look something like this, right? As you plug in negative numbers, they get bigger, and positive numbers get smaller. So it's decreasing over time. So part of your homework today is going to be like our first examples here. They're just going to ask you, is it growth or decay? But sometimes it can be a little tricky depending on how they write the function. So I want to kind of look at a couple of them with you and see if we can maybe figure out what's happening there. We only have 3 examples today. And 2 of the 3 are, is it growth or decay? What do you think about that? It's out of control. Which means everyone should get their homework done in class, I think. If we work. Okay, can we go? Not go. You gotta work tonight, Bryce? How many hours a week do you work? That's a lot of hours. Why do you work so much? Where do you work in? Like, do you work in the back usually? Like, you make stuff? So maybe one day you'll skip school and we take my order and then I can yell at you. You might have known that was me, and you ran away because you didn't want me to yell at you, and I saw you anyway. I saw you, so it wasn't a very good dog. Was it your class I was telling you about the Big Macs? About the how to order a cheap Big Mac? Oh, here's my husband's plan. Well, actually, someone at work told him this, and I was embarrassed. Yeah, he just said order a McDouble and order no ketchup, no mustard, add Big Mac sauce, and it's like a cheap Big Mac, because it's a 99-cent Big Mac with no extra bread in the middle. And then my husband went and he's like, I just want to try it and see if they'll do it. And I was like, I'm so embarrassed that you're ordering a McDouble with Big Mac sauce. And he was like, they just did it. It was no big deal. So then one time he made me order it, and I was ashamed to do it. But it's like a 99-cent Big Mac. And he said it tastes just like a Big Mac.
I do that and I get 50% off.
Oh my goodness, that's like a 50-cent Big Mac.
Yeah.
Try it. Make those people make a special thing for you. The bad thing is you have to wait for them to make a special one with Big Mac sauce. They just do it. They just say no ketchup, no mustard, add Mac sauce. That's what they're at. And you get a 99-cent Big Mac. Tell your friends, so we can all die of high cholesterol. That's what I tell my husband. I'm like, this is just worse because it makes you eat terrible food or cheaper than it was to begin with. All right, 2 questions on your homework today say this. State whether the function is exponential growth or exponential decay. And you have to think about it. If you think about the way the book says it, the book says look to see whether the base is bigger than 1 or smaller than 1. But I think this little -2 here makes it kind of tricky, right? So is that base bigger than 1 or smaller than 1? Because this is actually your base, right? 3 is your base, and I just want to throw out here that a lot of people want to say exponential growth because they say, oh, 3 is bigger than 1. But doesn't a negative exponent mean like it moves it to the bottom? So this is the same as saying 1 over be smaller than 1. It's 1/9. And so negative exponents for me, when I see a negative exponent, a lot of times I think, hey, that's exponential decay, but you still got to be careful on the base there. So make sure you look at the problem and think about what would that be, and since this is less than 1, we could say that that is exponential decay. Do you agree with me on that, or kind of confused on that? So in second hour, when we said this, someone said, okay, so if it's a negative exponent, it'll always be decay. Do you agree with that statement? Can you give me an example of something with a negative exponent that would not be decay? Yeah, what if you had like y equals 1/2 to the negative 2x? If it's already a fraction, and then you make it a negative exponent, do you agree that 2 is going to become on top and the 1 is going to go on the bottom? And so that would actually be exponential growth, because the negative like undoes the fraction. I don't know if that makes any sense or not. So these aren't supposed to be terrible problems, but sometimes I think they're really tricky. And so I just want you to make sure you don't always think every negative exponent is exponential decay, or think that every number that's bigger than 1 is exponential growth. Make sure that you think about it. So don't yell this one out, but think about this one for a second. What if I said 1/e to the x power? Think about whether that would be exponential growth or exponential decay. So how about, if you think it's growth, when I say go, put a thumbs up. And if you think it's decay, because it's getting smaller, put a thumbs down. Ready? Go. You're not doing anything. How could we write 1/e with exponents? Well, how about that, remembering that? 1/2.71 something. Is this number bigger than 1 or smaller than 1? It's smaller than 1, and it has a positive exponent, which means it has to be decay, right? Or we could think about this. Could I write this as e to the negative x? Is that the same as 1/e? So also, if you think about this being bigger than 1, that's a negative exponent. It's kind of the same as number 1. It's exponential decay. If you really get confused on this, you know what you could do? Plug in numbers and see what's happening. Exponential decay is getting smaller over time, and exponential growth is getting bigger. So if you get confused on this, plug in like 2 and plug in 5, and see, is it getting bigger or smaller? And if it's getting smaller, it has to be decay, and if it's getting bigger, it has to be growth. Maybe? A lot of mixed answers there, so I don't know how we feel about that. We'll talk more about this with population stuff tomorrow. The other thing today is just working with some population problems, which aren't so bad. It's kind of applying it. It looks a little bad, but just remember, this is my last slide on this next one, so don't cry too much when you see it. You got to write a little bit. Lots of applications for this. Today we're just going to focus on population applications. So go ahead and write this, and I'm going to pass out some calculators because I think we might need some calculators. If you don't have a calculator, I'll bring you. Who needs a calculator? Calculator? Calculator in this room? Calculator? So you're going to have a problem like this, maybe a couple problems like this on your homework, where they give you this population model. And actually, you've probably done this in biology or AP biology, where they give you this population model for either a population of animals or something. This is a logistic equation. We talked about this back in like chapter 1 when we talked about our 10 basic functions. Remember that population models can kind of be modeled like this, where they have 2 horizontal asymptotes. Like population can't be negative. Your population can only get so big. And they look something awful like this. Really important on these is you pay attention to what the letters represent. P is the population in millions, and T is the number of years since 1950. And I'm going to have two parts of this. Part A says how many people were there in 1950. So if we're talking about how many people there were in 1950, we have to plug in something for T. Am I going to plug 1950 in there for T? They're going to plug in 50 because T is the number of years since 1900. So 1950 means that you're not going to plug 1950 in there. You're going to plug in 50 because that's how many years since 1900. And you're just going to type that in your calculator. And I gave you all calculators because it's really important that you can use them correctly. If you want to type this all at once, especially my calculators, I know how they work. It works out fine. You can type it all in at once, but you have to make sure to put that denominator in parentheses. If you don't feel comfortable typing it all at once, do the bottom, and then take 12.79 divided by what you get. But make sure you keep lots of decimals to begin with. Like don't cut off those decimals until the very end. We call that round off error. So I'm just going to type 50 in as well, and we can see if we agree or disagree with our each other here. And E on my calculators is right with ln, or if you find your ln or log buttons, E should be somewhere around there. Like mine, you have to hit second to get to it. I got 8.456896623. Did you get something like that? Did you try to type it all at once? I'm pretty sure this is the answer. So try again. I'm going to put parentheses up here with your exponent just to make sure. Error. Uh-oh, I gave it away. Can you get it back or it's gone? Maybe you use, is this a minus sign or a negative sign? Did you have a negative sign? Oh look, I think you used a minus sign instead of a negative sign. Because that was a minus sign. I don't know. Who else can tell? I don't. How can I see the rest of what it is? I don't know. I have to watch which way they go. Just go to you. Okay, here's the thing. You have to put this in parentheses because you have to show that you want all of them things. You have to do now. Because what you were doing is it was taking e to that and then multiplying by 50.
Okay, well, like the first time I put the 50 in parentheses.
You need to put the whole thing in parentheses. What was wrong with yours? Oh, that might be a problem. Anyone else having calculator issues? You might say, why did you put so many decimals here? Well, remember what P is the population in millions. So you could just say that's like 8.5 million. But why, when you could give a really exact number, and you could say in 1950 there were 8,456,000, and we can't really have point so much a person, but we could round that up to about 897 people. And you might, like, if you look in the back of the book on one of yours today, you might say, how did they get all those numbers? It's just because they take the decimals after it. But notice how you enter it in your calculator is really important, and so that's why we practice some of this with our calculators. Eventually, we're going to do stuff where we're solving and LNing both sides and stuff that we did in Algebra 2, but today we're just kind of playing with our calculators. So what if I asked you, when was the population 10 million? That means I want to know, when does this equal 10 million? And so there is a way that we can solve this and do LN stuff and do all that, but they really just want you kind of guessing and checking here to get to the year. So let's try to get in the range here. Is our answer going to be later than 1950 or earlier than 1950? At 1950, there was about 8.5 million. So we know it's later than 1950, so I don't know. Someone tell me what they think. 1955? So someone can plug 55 in. Anybody else want to guess the number? 1960. Someone plug that in. What do you think? 1969. Someone plug that in. Let's see here. I have mine. I didn't do 55. Did somebody do 55?
I did.
70. I came really close to it. It's like 10 more.
Yeah, I think 1969 was like 9.9. Oh, let's see. I think 1960 first. And I got that to be about 9.29 million. And then I picked 1970. And I got 10.02. But I went back to 1969 because I was like, well, what if it was 10 million in 1969 also? But it was 9.95 million. So I think 1970 would be the better choice. There's one on your homework today. When you get to it, I'll help you. Ian will help with it, but I want to kind of give you some guidance here. There's one on your homework that talks about the carrying capacity. Remember in biology, that means like the biggest sustainable population. I might even say that in your book. So there's one in your homework that asks, what is the biggest sustainable population? And all they want you to do is pick some really big numbers for T and see what happens. Because it's going to approach, there's going to be this asymptote up here that if you kept picking really big numbers, like instead of just picking 50, if we picked like 500 years after 1900, we're going to be kind of at that sustainable population. And so we'll see how we do when we get there. But basically on that problem, they just want you to pick like 500 or 1,000 and see what happens, and maybe you'll notice something. There's also the very first one I want to help you with. So here's your homework. I want you to go ahead and write this down, get your paper out, and then when we're ready, I'm going to help you with 33 because it talks about limits and end behavior, and I normally tell you to ignore that part, but I think we could do today, so I think it's helpful. So go ahead and write this down and then get your paper out. And you don't have that many problems as you can see, and I'm going to help you with 33. So there should be no reason we don't all get our homework done today. Ben's not even here to get his homework done. So if you read the directions for 33 and 34, it says state whether the function is an exponential growth or an exponential decay function. That's just like our first example. But then it says, and describe its end behavior using limits. Well, we've described end behavior. That's where we say, like, as x goes to infinity, f of x goes to what? As x goes to negative infinity, f of x goes to what? A limit going to infinity is kind of the same thing. And I just want to show you how we can do this with exponential functions by just thinking about whether it's growth or decay. So step 1 on 33 is if I have 0.5 growth or is that exponential decay? Because this is less than 1, and it's a positive exponent, what do we say, growth or decay? It's decay. This is a less than 1, so if we plug in bigger bigger exponents, we're just going to get smaller and smaller fractions. So think about exponential decay is going to kind of look like this, right? Like this side's going up, this side's going down. So the second part of this, and the part that I'm going to make you do on 34, is the end behavior is just saying as x goes to infinity, f of x goes to what? And as x goes to negative infinity, f of x goes to what? They throw in the word limit there, but really, like, when we do end behavior, we're doing limits. I just kind of avoid that talk altogether. So let's do the infinity side first. Right, this is my XY chart here, sort of my XY plane. As I keep getting bigger and bigger values for x, what is my y value getting closer and closer and closer to, but never quite touching? 0, because we have that horizontal asymptote, right? So I would just say it's going to 0. And what about negative infinity on this one? As I go smaller and smaller values of x, what's happening to my y values? They're getting bigger and bigger, which means it's going to infinity. Will every exponential graph always have one side going to infinity? Will every exponential graph with no transformations going on always have one side going to infinity? Had to kind of restate my rule there. And this, will that always be your horizontal asymptote? Like one side will always be going towards your horizontal asymptote, the other side will be going up. And so on 34, I think you should have one of these 0 and one of these infinity, depending on whether it's growth or decay, because it just depends on which side's going towards infinity. All right, so that kind of just helps you think about that graph there. So I just did 33 for you. So you need to do 34, and then 56 and 57 are like population model stuff. 58 is just a little problem there about carbon 14, and then there's some true, false, and multiple choice. So really not much at all, and you still have like 16 minutes. So get this done. If you need help, let me know today, because then that means tomorrow I don't feel like we should have to do too many questions, because you should be able to get your questions answered today in class. Okay, if you still have other test correction questions, you could ask me those now too.